Okay, so today we're going to finish multiplicative weights. I just want to show you how you would apply it to linear programming to solve linear programs or approximately solve them. And then after, after that, we're going to switch into a new topic, namely flows. Okay. So, so right now I'm going to talk about, oh, and someone, yeah, so Eric just asked me, when are you going to get feedback for your project proposals? Yes, you will. So I think I should be done maybe by the end of Sunday, like end of the weekend, let's say. Okay, so I'm looking through those to give people feedback. Okay, good. So applying multiplicative weights to, let's say, LPs. Okay, so let's just remember the theorem from last time. So theorem, we said that if you use multiplicative weights to come up with the probability vectors in each iteration, you get the guarantee that your sum of expected costs over all the days, so this is mt dot pt. So pt is the probability vector you output over the experts in day t. mt is the cost vector on day t. Remember, mt, the ith coordinate of mt is the cost of the ith expert on day t. Okay? This quantity is at most the min over all I from 1 to n. So there are n experts of the sum over t of the cost of that expert on day t plus epsilon. So this is for any epsilon between 0 and a half. Epsilon times the sum of MIT absolute value plus ln n over epsilon. Okay, that was the theorem from last time. Okay, and remember we assumed that all our costs, these entries of these cost vectors, we assumed they're all between -1 and 1. Okay, so in particular, this sum is over all the days. So this sum is at most t. So you could also say this is at most the min over I of sum over t, MIT, plus epsilon t plus ln n over epsilon. Okay, and right, so this is true for all epsilon. So you can choose epsilon however you want. As long as t is, like, say, bigger than 2 ln n, for example, you can pick, for example, t to be, set these two things equal by choosing epsilon appropriately. And this thing will be at most the min over I, sum over t, MIT, plus root of ln n over t. Okay, so if you choose epsilon to be root ln n over t. Is that right? I seem to be off somewhere. Sorry? In the definition of epsilon?
No, in the square root.
Here? No, I mean, I want to say that if I play for a lot of days, my error goes down, right?
Oh, so you don't like choose. Well, that's what you get when you choose.
Right. Oh, I see. Okay. Oh, right. Then, yeah. So I guess normally people talk about maybe the average regret, and then that decays like 1 over t. So, for example, if you look at the average thing here, the average will go down like. Then I think this is okay. So you'll often hear people talking about like so this quantity here, the stuff beyond kind of the optimal bound you want, is called the regret in some literature. So people talk about trying to minimize regret. So you'll often hear people talking about kind of the square root t and loss in regret. Okay, so that's where this comes from. It's by a particular choice of epsilon running multiplicative weights. So, very good. So now let's apply this to LPs. So LPs, I want to have so I want to check feasibility of x in P and AX is at least B, where P is some convex set. And A is an m by n matrix. Okay. And I want to give a definition so we will be considering subproblems of the form does there exist an x such that P transpose AX is at least P transpose B for P a probability vector. Okay. A row-bounded oracle, okay, is an algorithm which, when given, when given this problem star, either okay, if such an x exists, output an x such that for all I, ai dot x minus bi should be at most rho. If no such x exists, it outputs infeasible. Okay. So notice that if the actual feasibility problem, if this problem is actually feasible, then because the entries of P are non-negative, this problem will also always be feasible. Oh, and also P transpose X should be greater than P transpose B, and X is also in P. So this feasibility problem is what the oracle should decide. Okay. And I just said if that's feasible, then certainly this is, because take an X which is feasible for this, and then just put P transpose on both sides, and by non-negativity of P, this inequality will hold. Okay. Questions?
Then the first point, you want to output a vector which is feasible for this subproblem?
Yeah, we assume that the oracle, when given, so the oracle is given P. The oracle knows, so it knows capital P, the convex set. It knows A, it knows B, and it knows little p. And then it wants to know, the oracle will tell you whether or not there exists an X such that this thing is, to make this feasible.
So the first point here should read for each I which is in subproblem is probability distribution. Not all the constraints are satisfied, only those for P is
Oh, I see.
So otherwise it would be just the same.
No. But this is an absolute value, right? It could be the case that ai dot x is less than bi. But the oracle just guarantees that the difference in magnitude is small. Yeah. Yeah, so I mean, you're right. So if I had said that, so really if I had said, this, where rho is positive, then this would have been feasible. But I put absolute values here, so I'm not telling you anything about which one is bigger between these two. Does that make sense? Yeah, so this x doesn't have to necessarily be feasible for the original problem. More questions? Okay. So now I want to tell you that if we had such an oracle, then we could get an approximate LP solver using multiplicative weights, and I'm going to describe that now, and then I'll go back to, I'll say just a few more sentences afterward about the example I gave last time with set cover to tell you how you could get such an oracle for set cover, for example. Okay. Good. So yeah.
This is still not clear to me.
Okay.
You can add a constraint which is like kind of far away from the whole physical polytope, and then this inequality, like, then no feasible point will be close to this constraint, right?
But you said, okay, so you said add a constraint,
Yeah.
which what? Which is far away
Which
from
is
the
far
feasible
away
region?
from the feasible polytope.
Okay.
The hyperplane is far away.
Yeah.
But like the whole feasible polytope is within the feasibility of this constraint. So like the point first, for what I understand it, means that if there exists a feasible point x, it outputs point which is close to all.
So wait, so when I say if such x exists, if an x exists which is feasible for this, for star. Yeah, okay.
It outputs a point x which
Yeah.
is close to all constraints for which this absolute value basically means how far away
Yeah,
from
yeah.
the hyperplane.
Right.
Then if you add a hyperplane which is far away from this
Yeah.
polytope,
Then your row might be terrible.
yeah.
Yeah. So you just get a bad row.
Okay.
Yeah. I mean, so, like, we're going to end up thinking of this t as being the number of iterations of multiplicative weights to get, some good error. So as t gets bigger and bigger, our error in violating feasibility will shrink. And the number of iterations we need will depend on rho. So in your example, if you're coming up with a polytope such that the rho has to be very large, it just means that multiplicative weights will run for more steps. Does that answer your question? Yeah. Okay, good. And any more questions? Yeah.
I'm a little. Is star x in p and ptax greater?
Yeah. So sorry. This capital P is the convex set. This little p is the probability vector, probability distribution over experts.
Star is both conditions.
Yeah. So exactly, it should both be in capital P, and this inequality should hold. Does that make sense? Okay. And notice, intuitively this seems like an easier problem than that because this has m constraints and this has one constraint. I mean, aside from the capital P business, right? This is right. These are just numbers. Okay. So good. So what are we going to do? So now let's analyze multiplicative weights for LP, and the theorem is that if we have a row-bounded oracle for rho bigger than epsilon over 2, then we can use multiplicative weights to find x and p such that ax is greater than or equal to b minus epsilon times the all ones vector in O of rho squared, I think rho squared d, rho squared, let me think, ln n, ln m over epsilon squared iterations. Or days, t. Okay. So let's see how to do that. So I need to tell you what the actual algorithm will be. So proof. Okay, so what are we doing multiplicative weights on? What are the costs? What are the experts? So the experts are the constraints. So there are m of them. Okay. The next thing is, what are the costs? So on day t, we have some pt. Right? Remember how multiplicative weights works. So we've gone some number of days. Initially, on the first day pt is just the uniform distribution on all the experts, right? And then gradually, as we've been running multiplicative weights, we change this pt vector. And now we're at some day t, and we have some pt. I want to tell you how I'm going to define the cost vector. So remember the theorem from multiplicative weights. MT can be chosen arbitrarily or adversarially. After you choose, just like before when we were talking about learning from experts, after you make your decision, the costs are revealed to you. Like who's wrong and who's right was revealed to you, right? So same thing here. After you choose your p vector, your pt vector, m is revealed to you. So I want to tell you how we're going to define m to ensure to make it do what we want to prove our theorem. Okay. We define the cost vector to be mt is 1 over d, or 1 over rho, sorry, times ax minus b. Okay. Or xt, where xt is the output of the oracle. Right, so we give the oracle pt, and we tell the oracle to give us back xt. Now, the oracle might say that there is no xt. Right? The oracle might say it's infeasible. But if it's infeasible, then if this is infeasible, then as I said, the original is infeasible. Right? That's the contrapositive of what I said earlier. Right? So if the oracle says there is no xt, we just halt and we say, sorry, this LP you gave me is infeasible. But if it gives us an xt, then we're going to define the cost vector in terms of that xt. Okay. And now what do I want to say? what do I want to say? I wanted to get confusing myself slightly. Oh, good. So now what I want to say, I want to say that MT dot product with PT, what is that equal to? That's equal to PT transpose times this thing here, 1 over rho, AXT minus B. Sorry, this rho sort of looks sort of like a P, doesn't it? Okay. Yeah, so I really don't like that. I should have noticed that this might happen. Let me just call this alpha, or let me call this gamma. Okay. Okay. Which is equal to, oh, and notice, right, so this thing is in minus 1, 1 to the m, okay, which the theorem needs. I mean, the reason we normalized by this gamma was to ensure that. Okay, so this thing is equal to 1 over gamma PT transpose AXT minus PT transpose B. And what can you tell me about this quantity? The thing inside of the brackets. Yeah, it's not negative. Right? I mean, that's what the oracle does. It solves this feasibility problem. So we know that this thing is bigger than or equal to that. Okay, good. So now, so this is one direction. We know that this thing, we know that this quantity is bigger than or equal to 0. But we also know that this quantity is smaller than or equal to something because of our multiplicative weights theorem, right? So we know that now 0 is at most 1 over gamma PT. Well, 0 is at most, let's say, MT dot PT. So we can sum over all t. And that's still true because each one individually is non-negative. And then now, let me now apply the MW theorem. This is at most. So let's say for all I, this thing is at most the sum t from 1 to capital T of mi of t plus, and I don't need the stronger version. I'll just say that this is at most epsilon t plus ln m over t. Remember, m is our number of experts, the number of constraints. And now let's expand this out. This is equal to 1 over gamma times the sum over t of ai dot x t minus bi plus epsilon t plus ln m over t. Yeah, thanks. And actually, I'm actually going to apply this. So I'm going to apply this with some a different epsilon than the final epsilon I want. So the final epsilon I want is this one. I'm going to apply multiplicative weights with some other error. Let's call it eta. Right? I can choose I can choose this error parameter however I want as long as it's less than a half. We'll see what eta is going to end up being. Okay. And then now, what I'm going to do is multiply by so now multiply by gamma over t. And what we get is, and set x tilde to be 1 over t times the sum over little t of xt. Right? Notice that by the feasibility condition from the oracle, each one of these is in capital P. So this itself, this average, is also in capital P by convexity. We assume that capital P is convex. Okay. So then, if you multiply both sides of the inequality by gamma over t, what you get is that 0 is at most ai dot x tilde minus bi plus gamma eta plus, yeah, this should have been eta, ln m over gamma ln m over eta t. Okay? Now what I'm going to do is I can set eta to be whatever I want. So I'm going to set eta to make this at most epsilon over 2. And then I'm going to set t to make this at most epsilon over 2. So now set eta to be, I guess, epsilon over 2 gamma. And now set t to make this at most epsilon over 2, which means gamma ln m 2 gamma ln m over eta. Right. Which if you plug in what eta was, this should be 4 gamma squared ln m. Oh, and let me put also an epsilon here, because I want this to be epsilon over 2, over epsilon squared. So all I did, you can verify this offline if you want. All I did was I chose eta and t such that, let me call this A and let me call this B, such that A and B were at most epsilon over 2. That's all this was. So now this implies that 0 is at most ai dot x tilde minus bi plus epsilon, which implies that ai dot x tilde is at least bi minus epsilon. Okay, so and this is true for all I. So that's it. Okay, so what do you do? So how do you use multiplicative weights to get an almost feasible solution to the original problem? You keep running this oracle at every step to give you an xt, and at the end of the day, your almost feasible x is the average of all the xt's that you've encountered so far. Okay, so this is your final output. Okay, so any questions about what I just said? You okay?
Yeah, I know you explained this like several times.
Yeah. That's right.
All right.
Star has two constraints. The first constraint is that x should be in P, and the second constraint is that little p transpose AX should be greater than or equal to little p transpose B.
But so what is this this closeness to the constraint in row I condition?
Closeness to constraint in row I?
Uh,
Oh, yeah, so you're saying...
is that something else on top of that the oracle returns?
If it's feasible, it'll return an x, and furthermore, the x that it returns will satisfy this property. You have that promise that the oracle behaves this way. Yeah, it doesn't just find any feasible x, it finds a feasible x that satisfies this property. Okay. So, just going back to set cover, I mentioned this last time, but we hadn't actually proved this theorem yet, so I didn't give you the details, but let me just finish that off, and then we can start on flow. Okay, so let's finish off set cover. Remember there, we had some collection of sets, and we wanted to choose fractionally sets to cover our universe of elements. So we wanted to minimize the sum over S of x of S, such that for all elements E, the sum over S's containing E of x of S should be at least 1, and also x should be non-negative. And Rp was going to be the set of all x's such that, first of all, x should be non-negative. And second of all, the sum over x of s's should be at most L. Or I think, did I say alpha last time? Whatever. Should be at most beta. Okay? And the point is, we know that if there are m sets, we know that opt is somewhere between 1 and m, right? So we could just binary search. So remember, the multiplicative weights theorem for LPs, it lets us get something that's almost feasible, right? There's no minimization here. It's just a feasibility question. So the feasibility question we're going to answer is whether or not it's possible to get cost at most beta. And then if you can do that, you could binary search on beta. Okay. So how would we implement? So the question, how do we get an oracle, right? We need an oracle to be able to apply this multiplicative weights idea for set cover. Okay, so we're given some p, and we want to check feasibility of p transpose AX is greater than or equal to p transpose B, and x has to be in this set capital P. Okay, so how are we going to do that? Well, first of all, what's P transpose B? Yeah, P transpose B is 1. Right? B is just the right-hand side here. And so P transpose of this is just the sum of all the PEs, which is 1. P is a probability distribution. So we want P transpose AX to be bigger than or equal to 1. Now, what's P transpose AX? Well, let's just write this out. This is equal to the sum over all E, PE, times the sum over all S's containing E of XS. And we can write this as the sum over all S's of XS times what I'll call P of S, where this is just the sum over E's the sum over e's and s of PE. Okay. So forget about the condition that the x you want has to be in. So ignore this condition for a second and just pretend this condition just says that the sum of the x's has to be beta. How would you choose x to maximize this sum? Actually, maybe it'll be more inspiring if I say pretend this beta was just 1, right? So x is specifying some convex combination, right? X is specifying some convex combination of these PS's, right? So then what would you do to maximize that convex combination? Yeah, you would place all the mass on the s that has the biggest PS value, right? So you can assume that, and since x is non-negative, I mean, if you normalize it to have sum equal to 1, then that argument is a real proof. Okay, so if you want to maximize, for x and p, to maximize the sum of xs p of s, choose s such that p of s is maximum, and set xs to be what? What would you set xs to be? Yeah, you said it to be beta. You place all the possible mass you could there. Okay, so that's what the oracle will do. Okay, so when the oracle is given this p, it's going to write down this expression. It's going to observe which PS is the biggest, and it's going to set xs to be beta. So the oracle picks x to be, beta times the sth standard basis vector, let's say. Yeah, sorry, this is the sth standard basis vector. Okay, and then that'll give you some value. It'll give you beta times p of s. And if that's less than 1, it's just going to say it's infeasible. I maximized it and I couldn't get 1, so it's infeasible. Otherwise, it'll give you the point. Okay, so if p of s is less than 1, we output infeasible. Otherwise, what can I say about the row? Remember, I want to have a row-bounded oracle. What can I say about the row that this thing satisfies? Otherwise, for all constraints E, I want to look at AI dot x minus bi, and I want to bound this, right? Or let's, for all constraints I, maybe, but the constraints are indexed by elements of the universe. What can I say about this quantity, right? I need to understand this to know how many iterations I need in my multiplicative weights algorithm. Well, this is 1. So what can you tell me about this value? Right, so what is x? X is just beta times the sth standard basis vector. So I claim there are 2 cases. So let's say for all constraints E, I want to E is an element of the universe. This is in the universe. So there are two cases. Either E is in S or it's not in S. If E is not in S, what's this dot product, given the x that we're outputting? It's 0. Good. In which case, this difference is 1. What if E is in S? What's this dot product? It's beta. So this thing is at most the max of 1 and beta minus 1. Actually, yeah, okay, good. Which, let's just call this, beta, we're binary searching to get beta anyway, right? And we know the answer, we know opt is between 1 and m. So we're going to be binary searching between 1 and m. So beta is certainly at least 1. So let's just say this is at most beta, which is at most m, for example, the number of sets in our input. Okay. So this tells us if we combine this with our theorem, which I think we erased, well, that's the gamma here, right? So the number of iterations we need of the multiplicative weights algorithm is going to be something like m squared log m over epsilon squared. So this implies O of m squared log m over epsilon squared iterations of multiplicative weights. Okay. To get a good solution to fractional set cover. And remember we said that for fractional set cover, if you're violating the constraints by epsilon, you can rescale and get an actual feasible point. But your cost will increase by a factor of roughly 1 plus epsilon. So you can get a 1 plus epsilon approximate solution to multiplicative weight, to fractional set cover, by just doing this number of iterations of multiplicative weights. Okay? So that's all I want to say about multiplicative weights besides p-set problems. But do you have any questions before I change topics? Yeah. Sorry, can you say it again?
You said that the theorem is only true when A has non-negative entries, or you don't need that assumption?
I don't, like in the proof of the theorem I did, so before we moved to set cover, in the proof of that general theorem, I don't think I ever used that the entries of A were non-negative. I mean, sometimes that can help you to implement oracles, right? So at the end of the day, you have this general theorem, but to actually make it work for your problem, you have to be able to come up with a P, and you have to be able to implement an oracle with a good row, right? So just because you have the theorem doesn't mean you can always use it effectively. But yeah, I guess to answer your question, I did mention last time that kind of this idea was developed by in a paper by Plotkin, Schmois, and Tardosh, and they were considering packing and covering LPs. But if you look in the Aurora Hazan Kala monograph on multiplicative weights, yeah, I mean, there's no requirement for that theorem that it be a packing or covering LP. Okay. So, new topic. So flows. Okay. So, since CS124 is a prereq, I will assume I'm not gonna. So, you will be able to follow what I'm gonna say without knowing the details, but there are certain details I'm not gonna prove. I'm just gonna assert they're true, and if you know the proof, great. If you don't, you can go read about the proof. Okay. So flows. So we're given a directed graph G equals VE. And we're also given capacities and the capacities are all non-negative. Okay, and we're also given a start vertex S and end vertex T. Goal is to output a flow vector I'm going to define what this means. A flow from S to T a feasible flow from S to T obeying the capacity constraints. So let me start defining some of these terms and also drawing pictures. Okay, so definition. A flow, F, okay, it's, so for me always, so N is the size of V and M is the size of E. And I'm always just going to assume that the graph is connected. If not, then you can do a DFS in the beginning and only work with the connected component that contains both S and T. So in particular, since the graph is connected, M is at least N minus 1. So I'm always going to think of M as being at least N whenever I write bounds. Okay, so a flow is a vector, let's say an ST flow. So 1 F should be non-negative. 2, for all V that are neither S nor T, the sum over edges UV in E of the flow of E should equal the sum of all the edges VU. So this is, I'll say this is flow in equals flow out. So it's also called, conservation of flow. We also want, so S and T are special. We want that, so I'll draw a picture soon, but imagine that we're trying to ship water from S to T. Okay, so water is flowing out of S and then it's landing in T. So what we want is to say that the amount of water that leaves S is equal to the amount that enters T. Okay, so that means that the sum over all edges E being SU of FE is equal to the sum over all edges E equals UT in the edge set E of FE. Okay, so flow out of S equals flow into T. Okay, and we say F is feasible if for all edges E and E, FE is at most the capacity of that edge. Okay, and the value, let me write the value of F, which we'll write val of F, is equal to the amount of water we ship. So you can imagine, for example, we have a graph. So here's an example. This is S, this is T. These are two other vertices. And let's say all the edges, let's say there's cell centers like this. They're all directed in this way. And let me also write down the capacities of these edges. 1, 1, 1. Let's say they all have unit capacities here. So one flow is, one feasible flow is the zero flow. I won't ship any water. Okay. Another flow, for example, is I'll ship 1 unit of water here, this way. And then I'll go down here, and then it'll go this way. And I'll say I'll ship 1 like that. That gets me 1 unit of flow. Another thing I could do is I could just go this way, send 1 that way, and send 1 that way. Is that purple visible? I feel like it's very dark. Right, so this purple flow has a value of 2, whereas the yellow flow has a value of 1. Right, so if we're trying to maximize the flow, the purple flow would be better. Okay. So also I should say in this goal, we want F has maximum value. Okay, so we want to find a max flow. Now, pretend you've never heard of flow before. Okay. Given all the things we've been studying so far, how would you think to find a max flow? Linear programming, right? So this is exactly a linear programming problem. So LP formulation. We want to maximize the sum of all flow, leaving S. We have certain constraints. F has to be at least 0. For all E, FE has to be at most CE. And then we also have the conservation constraints, right? Constraints 3 and 2. But those are all linear constraints anyway. Right, so plus constraints for 2 and 3, I guess. Okay. Yeah.
I don't understand why you need constraints
3?
because if the flow is conserved at each vertex, then it should always be the case.
Oh. Yeah. You're right. That's right.
Isn't it that constraint 3 is basically equivalent to the constraint that no flow is entering the vertex S?
That no flow is entering S.
Or same as no flow is going out of vertex T?
Oh, I see.
actually need some form of free.
I think
It could rephrase that.
Also, it's so very because I think it's only true when you have no edge between yourself.
Oh, I see. Okay.
do not take into account the
I see.
two do not take into account
I see. Okay. 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 So. Yeah. So we could solve using simplex or ellipsoid or interior point. So okay, so in simplex we know we don't know any polynomial time implementations of simplex, right? We don't know any pivot rules that are guaranteed to run in polynomial time. Ellipsoid ellipsoid will run in polynomial time. It will also depend on. So I don't think I gave the. I didn't write explicitly what you get at the end of the day, but remember that you start with some ellipsoid containing it, and then you keep shrinking it, shrinking the volume of this ellipsoid over various iterations. The number of iterations you need will depend on precision issues. I think I did say that in class. So it will depend on like the log of the biggest capacity you have. Okay, so you'll have like poly n times some poly log in the largest capacity. Let's look at interior point, because I think that's one that we actually, some fast algorithm that we actually did go through in class. So the number of iterations is like root m up to this log factor. Well, let's let L, the precision absorbed log factor. So root m L iterations. In each iteration, O of 1 Newton steps. So what is a Newton step? I mean, do people remember in general interior point? So remember in general interior point, we want to minimize f of x. And we said that the change, x1, is going to be x0 minus some quantity. This is the current iterate. This is, you should think of these as flows. Right, so, I know, let's just call them x's. Okay, so next iterate. Right. Do people remember what the step is in Newton's method? Yeah, so the 1 over L is from gradient descent. Yeah, so you take the Hessian inverse, apply it to the gradient. Okay, that's Newton's method. So remember in linear programming, we said that in linear programming, this Hessian inverse was equal to something like, I believe, A transpose slack x minus 2A. So, I mean, you can also think of this as like Hessian the Hessian applied to x1 minus x0 should equal some particular vector. So, like in each step of in each iteration of Newton's method, when you apply it to linear programming, you're solving a linear system. Okay, so iterations of Newton's method for LPs in interior point method are linear system solves. So that implies total time. Well, root m iterations. Each one is a linear system solve. That's like m cubed time, or m to the omega using fast matrix multiplication, times L. So let's call that O of m to the 7/2 L. And this L you can show for flow problems. It's possible to for such flow problems always make this thing polylog of the maximum capacity U. This is the maximum capacity. One thing I will say is kind of the dominant term here, if you notice, is these linear system solves. This is for an arbitrary LP. It turns out that if you write the linear system solves you have to do for the particular case of the flow problem, the linear systems you get are a special subclass of linear systems. They're not arbitrary linear systems that you have to solve. Okay? And that was exploited in a paper in 2008. So by Deitch and Spielman. Stock 2008. Showed O tilde of m. O tilde is hiding polylog factors, polylog m factors. O tilde of m linear time when A comes from a flow problem. Right, so it's not an arbitrary A. It's not coming from this. Basically, it's related to, if you've ever heard of Laplacian system solvers. So I'm not going to, if you've heard of that, great. If you haven't, you can go look at their paper. But yeah.
Wait, so is this, they showed O tilde of m time for the overall thing or for?
This m cubed.
Oh, okay.
So this m cubed basically turns into that, which at the end of the day means they get an m to the 3/2 algorithm times log capacity, or polylog. I think they get log squared capacity. M to the 3/2 times log squared capacity for linear programming, max flow. Actually, they look at more than just max flow. They look at other flow problems as well. Okay, so that's great. But even without Deitch Spielman, you could apply IPMs. You would just get a terrible polynomial. You would get m to the 3.5. Okay, so without. Oh, and actually, I should mention when we were covering interior point, I mentioned that this barrier function that we were using, it weighted all constraints the same, right? We had a sum of log of the slack of the ith constraint. And I mentioned that this was kind of weird because if you repeat a constraint multiple times, you're counting it more, but really that constraint only matters once. And I mentioned that there's this paper by Lee and Sidford, which figures out weights to apply to that to make it run faster. And they showed that using their methods for interior point, you can actually turn this root m into a root n for max flow. So you get an m root n algorithm as opposed to m root m, right? And m could be as big as n squared. Okay. But so without, let's think purely combinatorially and not use any of this linear programming technology. So without LP technology, so Ford and Fulkerson. Oh, actually, yeah. So Ford and Fulkerson. I don't remember exactly. I think it's the 50s. I forgot exactly which, when, and where. Gave an algorithm with time O of m times f star. Okay, so I'm going to abuse notation. A flow is a vector, it's not a number. If I just write it without the val, I just mean the value. So the value of, so f star is the max flow. It's the flow that achieves the maximum value. And this is the value of that flow f star. Okay, so the running time was m times f star, which is not great, right? So for example, imagine, well, their algorithm would actually do great on this graph, but imagine I have ST. According to this bound, their algorithm could take time 1 billion, even though the graph has 2 vertices. It wouldn't take, I'm not going to describe their algorithm, it wouldn't take 1 billion steps on this graph. But for example, if you just modify this graph slightly, and then put 1 capacity here, their algorithm could take 1 billion steps if you're not careful. Okay, so okay, good. But if your capacities are all 1, then that's not terrible. And actually, I probably will end up saying what their algorithm is, just because I want to define certain terms. So what does their algorithm do? So this Ford-Fulkerson algorithm finds augmenting paths Okay, so what's the idea there? So we're given G, and we find some flow, some feasible flow. Okay, so what's a simple way to find, if there is one, what's a simple way to find a feasible flow that has strictly positive value? I guess maybe people have seen flow, so maybe people are shy to just say things that everyone knows. But you could just DFS. Okay, so e.g. DFS from S to T. Now you get a path in the graph from S to T, right? And that path has some minimum. When I say DFS, only consider the edges that have positive capacity. Okay. Do a DFS on that graph, a depth first search. Now you'll find some path from S to T. That path has a minimum capacity on it. So just put that minimum capacity on the flow, right? So to find some path, whose, let's say, min capacity edge is, some lambda. Now, define F to be lambda on that path and 0 otherwise. So, like, for example, sorry?
So lambda is...
Yeah, so I guess all I want to say is, so we have some graph. This is S, this is T. Okay. There's some capacities. No, I'm just making up numbers. Okay. There are some capacities on these edges, And I just want a DFS from S to T to find some path. So maybe I find the path that goes here, then here, then here. So this path has 3 edges. The 7 capacity, the 5, and the 2. I'd like to push flow along this path. But how much flow can I push on this path before I become infeasible? Well, I can push 2. Basically the minimum, right? So lambda here is 2. That's what I meant. Right? Okay, great. So now so now let's say we find some flow in G. So given flow F in G, yeah.
Do we always assume that the guarantees are integers?
Yeah, so I'll assume that capacities are always, so there are some rational numbers that I'm storing on my computer. I'll clear denominators, and I'll just assume that they're integers between 1 and u.
So, if you clear denominators, does the running time go up when you multiply everything by a certain
Yeah.
amount?
In Ford-Fulkerson. Yeah. So given a flow F and G, we can define what I call residual graph G of F on the same edge set where let's say the capacity, let's say capacity prime, this is the capacities in GF. The new capacity of an edge E let's say capacity of the edge UV, where say we have an edge E as UV, is going to be the old capacity minus the flow along that edge plus the flow in the opposite direction.
So, the flow in the opposite direction, is that across a different edge, a different directed edge that happens to go the opposite direction, or are we maintaining 2 separate flows for each edge?
Yeah, so our flow vector, let's just imagine that every edge that is in the graph, the reverse is also there. So if the reverse was also there, then it was already there, great. If it wasn't, put it there with 0 capacity. Okay. So yeah, imagine that we have edges in both directions for every edge. I mean, you can imagine if you want even that it's the complete graph where edges that don't actually appear have capacity 0. But I don't want to say it like that because I want our running time bounds to depend on m. But yeah, so for every edge that appears, imagine it appears in both directions. Maybe one of the directions has capacity 0. Does that make sense? And so what Ford-Fulkerson does, yeah.
So is that true in the quantification over E as well? So like you're defining the new capacity on these phantom edges every in the residual graph as well? Like, or are you just using the flow
So yeah, I'm defining a new capacity function in terms of my flow f, and this is how I define it. Yeah. Okay. Or is it? Any more questions? And by the way, this flow vector f is, remember, it's non-negative. So I'm not imagining that f u v is minus f of vu. Like, it might be the case that f of uv is 5 and then f of vu is 0. In fact, you can always assume that one of them is 0. Right? So for example, if this were 5 and this were 1, that's the same thing as just saying that this were 4 and that were 0. Question? In the sense that it would still satisfy, right? If any edge and its reverse both had positive flow on them, I could just make one of them 0 and subtract from the other, and it would still satisfy all these constraints. And it would give you the same exact, yeah, it would give you, yeah.
Wait, so if the reverse has positive flow,
Oh.
why not just see that as negative flow along the ordinary?
Oh, wait. Let me just be more careful about what I'm. Oh, sorry. Say it again.
If the reverse edge has positive flow, why
Yeah.
not just think of that then as the ordinary edge having negative flow?
If the reverse has positive flow. Oh, I mean, no, I want. So my definition of a flow is that it's a non-negative vector. Yeah, I mean, what you're saying makes sense, but I want to stick to a particular definition of flow. In my definition of flow, it's so yeah. You could so for example, imagine you have your pipe with water going in it, and the water's going in that direction, and it's going at a rate of I don't know, 5 liters per second, whatever your unit of flow is. So let's say it's 5 liters per second. That's the same thing as saying there's actually 12 going this way and there's 7 going backwards. But I mean it's both of these are equivalent. I will always just assume one of them 0, or it's the same as saying that 5 are going this way and 0 is going that way. Yeah. So I hope I didn't create any confusion. I'm just trying to state my what do you call that? My standards, not notation, but in my notation, there's always going to be, amongst an edge and its reverse, only one of them is going to have, at most one of them can have a non-zero flow on it. And also, edges appear both forward and reverse. One of them might have 0 capacity.
So,
yeah, in the beginning anyway.
What?
Oh yeah, go ahead.
Is that true since we started talking about flows? Like the whole discussion there with this reverse edges, or is that just for the purpose of flow?
Just assume it's not going to really. Yeah, let's say everything I said is always the case. This is at most going to double the number of edges in the graph, right? And all our bounds are big O of m something anyway, so it changes things by a constant. Okay, so are we everything? Okay. So Ford Fulkerson, what it does is initialize f to be 0, and gf is just g, right? By that definition. While there exists, and then there's a loop, while there exists a path, an augmenting path, in GF, we're going to let f prime be some flow in GF. And we're going to set our new f to be our old f plus f prime. And then we're going to set GF let me write it, GF to adjust the GF to the new f. Okay. So this is Ford-Fulkerson. And so it relies on a theorem. So correctness relies on a theorem, which is as follows. So F star is a max flow if and only if GF star has no augmenting path. Meaning that there isn't, S and T are disconnected. There's no path from S to T in GF star. Okay. So I'm not going to prove this. You know, it was proven in 124. You can find it in any algorithms textbook, intro algorithms textbook. But this is kind of, I state this theorem because we're going to use it for other fancier algorithms soon. Oh, okay, and it's exactly 4 o'clock. So next time we're gonna use this theorem to show that there are some faster flow algorithms than Ford-Fulkerson.